Hey folks, welcome to High Performance LLMs First Principles. I'm Rafi, and in this class we're going to learn how to achieve the best performance in LLMs, and that means both inference, so achieving high throughput during inference on relatively small systems, and achieving high training throughput on up to very, very large systems, tens or possibly even hundreds of thousands of chips, predicting and profiling. So the three pieces to write them out is we're going to write the code, we're going to roofline, so both fundamentally doing it in a spreadsheet or doing a little bit of arithmetic and an algebra, and then we're going to profile. We're going to run the code. We're going to compare it to the predictions, and we're going to make sure we know what's happening in the system. So really, overarching arc, though, is we're going to build an LLM from scratch in JAX that achieves kind of high performance on training and inference in both a multi-host and single-host setting. And it's about JAX, it's about LLMs, but really, it's not my intention in this class to really be purely about JAX and LLMs. We're really going to cover a lot of the foundations, and it's really meant to be about all of high-performance computing. It's about to be about GPUs. It's definitely friendly on TPUs, and as well as GPUs, and even on CPUs. So the goal is to really understand all of the basics, so you can make your own decisions about performance and really understand it deeply. So I taught this class something similar to it about a year ago, and the number one feedback I got so many times was things made sense when you were talking, but then I forgot. So to make that a little bit easier for folks, I'm going to provide materials between sessions, and hopefully you can take a minute, do it, plus your understanding, and if necessary, definitely ask questions. So my asks, so first of all, this in class, in session, feel free to ask questions, just raise your hand. I'd love to answer any questions. There's a Discord. If you want to know what's going on, I'll definitely post the assignments, post updates all on the Discord, so please join the Discord. If there are topics you're interested in that I'm not covering necessarily, please just message in the Discord. I've added a link to the website here, and then please do the exercise. Just let me know how they go. I'm hoping this can be kind of an enduring resource, both for folks who are entering the JAX ecosystem, whether on the cloud TPU and GPU team within Google or outside of Google. So to start maybe with my background quickly, I'm at Google on the cloud TPU and GPU team. At Google, I drive the development of MaxText, which is an open source reference implementation for large language models that achieves high performance. And two of the cool things we've done is we demonstrated the largest job, the greatest number of accelerators ever deployed for a single ML job, 50,000 accelerators, achieving high performance last year. And our team also has popularized and developed technologies for accurate quantized training. So training these LLMs in integer 8 matrix multiplies instead of in traditional floating point matrix multiplies that allows us to get better performance. Before that, I've done a lot of things in the accelerator world, TensorFlow, PyTorch, MXNet, TorchScript, TensorRT, my fair share of general purpose GPU, lots of on-device ML using Jetsons with great times, and then prior to Google, I worked on the Trainium compiler, so the compiler for AWS's ML hardware. Cool. So in terms of you enjoying this class, thank you all for joining, first of all. But what I'm hoping is you'll be comfortable in Python, so you're just comfortable reading and writing Python. Ideally, you'd have some ML experience, so whether that's TensorFlow, PyTorch, JAX, or another framework, use it from scratch, all good. And then you ideally need access to either a machine with TPUs or NVIDIA GPUs, or if you're really brave, you can definitely do it on a CPU, but you'll just need to be in touch on the Discord. So Google Earth and Colab is like totally great. I think you can get a Colab no problem with TPUs. And external folks, lots of good options there. Cool. And then finally, like just giving the overview of the class, here's like the heart of what we're going to cover. So in this class, and maybe maybe a bit of another one, we're going to build an LLM from scratch. And as in that session, the follow-ups, I'm hoping get you to do some things in that code base, and hopefully that let you feel like you're comfortable with an LLM. Then we're going to really do the fundamentals of high performance computing. And we're going to do those fundamentals both for a single chip roofline and then really distributed computing. That's like really the heart of what makes it interesting and really challenging, is making these computations work on thousands or even 10 chips. It can be quite hard. Then we're going to do a deeper dive into what happens on training, really talking through every step that happens in training, understanding the rooflines, the sharding and the optimizations. We'll do the same for inference. We're going to deep dive into attention. So attention is the core of what makes these neural nets really, really interesting. We're going to understand really what's happening there and what those optimizations you've probably heard floating around are. So flash attention and page attention, or VLM, continuous batching, lots of thoughts of what's really happening with an attention. And along the way, I'm going to try to cover some of these topics. So quantization, checkpointing, lots of practical tips. And we'll think about some of the other challenges that show up. So good put, ahead of time compilation. And then we'll go really, really deep. What I would really love for this class to do is to totally destroy all of the magic in ML and ML performance. So you feel like you're able to get all the way down to the hardware level. And to achieve that, we're going to cover two things in JAX, shard map and Palace, that within them really let you control exactly what the TPU does for you. And then finally, like, why are we doing this in JAX? So I think, first of all, I think the proof is in using JAX, or hopefully after the class, that'll make sense. But it's a beautiful way to write code. It's very Pythonic. It has really, really important advantage of being designed for end-to-end compilation. And we'll see why end-to-end compilation is so, so important as we go through the class. It works well on many, many platforms, so CPU, GPU, and TPU. We're hoping for it to work well on more platforms in the future. And I think you can just see it in the action. If you go to MaxX, you go to Megatron LM, those two code bases look really different. And I think that the fact that MaxX is able to target GPUs and TPUs, and maybe more platforms in the future, is like one of the really strong signs of how powerful JAX is. So hopefully you'll understand and be convinced by this after the class. Cool. So before we jump into today's like real content, just want to open the floor. Any questions? Anything people want to see? If not, I'll just jump into the real material for today. Cool. So we're going to try to code an LLM from scratch. And that's just going to be what we do today. Let's just see if I manage to share my screen properly. Cool, cool. Can folks just confirm things are coming through on the screen okay? Thank you, folks. It's a bit small. Thank you. I will make it a little bit bigger. Fonts are small. Yeah, thank you. And did someone raise their hand? Perfect. Okay, let's get started. So we're going to bounce back and forth between these two things. Let me get this video out of the way. And today it's just going to be programming, right? We just want to program an LLM in JAX. So the key is to do just training for this LLM. And there's going to be a series of steps we have to do to get through that. So we're going to need to define the task. We're going to have to define the different pieces we can build for this LLM. We're going to build the pieces one by one. We are going to skip a couple details. And then that's going to be a train loop. It's going to be very much the most basic transformer you can imagine, or maybe a little bit stripped down from what we'd really call a transformer. And should be good. So what's the task? I think as LLMs have become more popular, we've seen this, and maybe it's not new to folks these days, but the task is we first have to load this text. So in this case, so long and thanks for, and then we have to make a prediction, a machine that predicts long and thanks for all. So it sees the first n character, so long and then it predicts for, or it sees so and it predicts long. So the first thing we're going to do is do data loading. So we get an input, it looks something like so long and thanks for, and then we want an output. And it's just a matter of matching those two pieces of data. So there needs to be a little bit more thought about what this really means on a computer, because so long and thanks for are words, and they aren't necessarily representable on a computer. So the first thing we're going to do is we're going to tokenize. We're going to turn the words into numbers. So I'm just going to go do that, and we're going to simplify it. Instead of turning the so into a token, in this case 17, we're just going to use an ASCII transformation. So we're going to literally just get the alphanumeric character for S, uppercase S, and that's what we're going to put in there. And the reason why this is a good approach is, I mean, the neural net can still learn from it. It's not as good as other approaches. So tokenization does serve at the word level, does serve a purpose, but it's not necessary for an LLM at all. So we're going to get started here. And just so you know, I'm doing this live, so please, if I'm doing something wrong, speak up, and we can get that fixed. I will really appreciate tips as I go, because I will get stuck. So first, I've cheated a little bit, and I've given myself access to a data set. So before I'll just run this once so everyone can see it. And let's just see what the examples in the data set look like. While we wait for this to come in, let me just check if there are any questions or anything. Lost you all. Cool, no questions. So we'll run this, sounds good. Off to a great technical start. Yeah, you can just hop in if someone's asking a question. I think you can just hop in.
Is it easy to explain or quick to explain what tokenizing would be used for, rather than just a simple ASCII transformation?
That's a really great question. Thanks for asking it. So the reason that we care about tokenization is the context length of the neural nets is fixed historically. So we can support only, say, 2,000 tokens in the LLM historically. So instead, the advantage of tokenization is by supporting a dictionary with more words, you can support a greater number of tokens. So you might be able to support, 2,000 words instead of 2,000 letters, and that's in practice, 14,000 characters. Does that answer the question?
Yeah, that makes sense. Thank you.
I'm seeing some folks who are saying that the Discord invite link is showing as invalid. Hopefully I can help there right after this. Oh, thank you, Jen. Julie, I see your hand up.
Yeah, just on the tokenization dictionary. What about tokens that have never been seen before? I've seen like LLMs that properly can recognize those. So I'm just wondering.
That's a really fantastic question, and that really was one of the key ideas that made LLMs work well. So the key is that the tokenization can be learned to be partial words. So for like some things, it gives you a whole word. For example, like a dog is going to be its own token, but suffixes and single characters are also words. So if the token isn't in the neural net's dictionary, it will spell it out just like you or me. And ultimately, it will eventually have character level control. So it can always do things at the most granular level, even if it usually does not. Does that help, Julie? Cool. And then, Kellen, did you already ask your question? Awesome.
Yeah.
Great questions. Really, really appreciate them. Yeah, and you can see Pate is telling us about some fun subwords. Ing, ly, ish, est. Cool. So I just printed out our first batch, and we really aren't getting it. I just really want to I don't want to show everyone how to load a file from a dictionary, from a database, but all we're doing here is these are just examples. These are just strings. There's really nothing to it. I hope everyone sees that. And what we have to do is we have to turn them into a data set. So we'll just write that. So let's just write it. It's like def We should probably
What's the nature of this data set?
This is LM1B. I don't know what it has. Obviously, it's extremely important to have good data for whatever you're trying to do. But I actually don't know too much about this one. So we typically, for like custom companies, curate their own primarily. Any more questions? It's a good question. Cool. So all this is a text object that we're getting, and we'll just, I believe that we can just get into this thing. I'm just poking around to figure out what is in here. We're just going to convert this, and this is like really all we have to do. We have to just convert this into an NumPy array. So hopefully, with just 1 second of thought, we'll be able to convert it into a NumPy array. I can always cheat and look at my prior work if we have to, but shouldn't be too hard for us. NumPy.array. Okay, looks good. So this thing looks like, so they've already given it to us as a NumPy array. Even. Awesome. So what we want to do is just convert it to ASCII. So I've given us a function here that will just convert into ASCII. It looks like it's as simple as just converting the text into ASCII. Good, probably. And then we have to choose a max length. And I've given us a list of constants here. So I will choose our sequence length constant there, and everything will be padded to a fixed length. Okay, and I am forgetful on how to manipulate this object. Sorry, if anyone's hands raised, feel free just to, I'm not going to even check hands, just pipe up, okay? Oh, this is sad. Well, cheer. Let's just see a conversion there. Sorry, just dot numpy. Okay, cool. We can do that. So let's just look at example.numpy, example text.numpy. Usually perfect. And then hopefully we can see converting that to ASCII. Cool. So here we are. This will give us the raw data, the raw input. And then what we really want to do is decide how to generate the outputs. So def input to output. And this is actually as simple, and we'll call this raw output. This is actually as simple as just, as we saw, moving everything over by 1. So this is NP array. And all we have to do is np.0. So we have to make a 0 array. We are processing these things, and maybe we should just talk about sizes for a second. We're processing these things as being 384 by 128. And the reason for that is because we have a batch in sequences of 384, a sequence length of 128. So what we want to do is just slide everything over by one column. So we'll start by making something here. So batch in sequences, sequence length. And this will just give us an empty array. So empty zero array. And what we have to do is slide everything 1 slot to the right. So 0 array, all the whole batch. And we want 1 to sequence length. So almost everything except for 1. So just be set to be NP array, colon, 0 to sequence length -1. Okay. And then this will be, and we can just return the 0 array. And let's just run this again. We can see how we're doing. Input.
I think Julie has a question.
Oh, sorry. People just hop in. Thank you, Sky. But people just hop in too. What's the question?
Yeah. So I'm just wondering about the choice of ASCII encoding. Does this like limit the LLM training to like only Latin-based
100%.
Or
yeah, I would not recommend this in the real world.
A multi-byte character encoding for like multiple language training. Okay.
100%. 100%. Sorry. We're taking some liberties here. Again, also you would use, in all seriousness, you'd use this byte pair encoding to the strategy that folks tend to use for multi-token, which is fully Unicode aware. Yeah, great question. This neural net, I don't think we're going to ship in production. Just full disclosure. And then to answer your question maybe even a little bit better, Julie, you could still do it byte by byte and just handle the Unicode properly. That would also be a way of representing Unicode totally appropriately in an LLM. So when we look at raw output, we have this, and we can see that this starts with 84. So I've looked at one example. We have output. And it should just be everything just shifted over by one. Looks good. And if we just want to make sure we're doing the right thing, we can look at maybe example text 0 maybe. The shutdown was AIM. So the first character is uppercase T, and we can even just look ASCII character table, and hopefully the ASCII character table will tell us that T is 84, and that is in fact where we're going. And then our starting character was 84, so all is good. And the way this actually really should be called the outputs, and then this should be called the inputs to the neural net, right? So just to remind ourselves about what's happening here, the first token is 0, so that's like a empty token, and we're saying please predict 84. Now once you've seen 0 and 84, please predict 104, and 104 is lowercase h, and that's what the LLM is being asked to do. So I mean that is a totally acceptable data pipeline for an LLM. A little bit simplistic, but totally appropriate. So before I jump on to the next steps, any questions about our data pipeline? Cool. So the next thing we want to do is do embedding. So the neural net sees these 256 possible characters, but what it really wants to do is think about them as being vectors. So we're going to make a table that maps each of the 256 characters to an embed vector and does the lookup table. And it will just replace them by their various embeddings. So to do this, we're actually going to use Flax. And Flax is a helpful library in JAX that just lets us represent this. So I've defined our model here. We'll start with just an embedding. So the embedding will be by self.param embedding vocab to embed dimension. And the way this will work is we have to do jnp.asArray. So data np is JAX numpy as array embedding. And then hopefully we can just look up X. And the output for this should be batch sequence embed. So we will print out x.shape here, and we can see that in a second. So what we have to do here is just initialize our model, and there we're going to have to do our model. Model equals our model. We're going to need a random number generator. So this is a very important thing in JAX, which we'll cover later on, is why you manage your random numbers so carefully. And then we're going to initialize our model. So model.init RNG key, and then we need to just do something of the right shape. So init needs to know how big our inputs are. And recall that our inputs are supposed to be batch in sequences, sequence length. And then so that's going to be a pair representing the size. And then D type equals GNP, so JAX, NumPy, and we want them to be unsigned integer 8s. So that should give us our params. And then with that, we actually should be able to do a model.apply. Let's see how that goes for us. It should be model.apply. I believe it's going to be params inputs. And now this should make our predictions, though, of course, these won't be very good predictions. Cool. So I'm sure there'll be some debugging here. Cool. So this is an error saying that when we're doing our indexing, indexer must have integer Boolean type, but we're getting float 32s. So that's the same error as in Python. And one of my goals here is just to make JAX like a little bit less mysterious, is if you did this and then you tried to ask for the 2.5th element. Those indices must be integers or slices, not float. Fair enough, JAX. So we have to here up top, when we initialize our 0 array, it needs to be an integer here because we are restricting ourselves up to 255, 0 through 255. Cool. So x.shape, which we saw up here, is now 384, our batch and sequences, 128, our sequence dimension, and then 512, our embed dimension. Looks good to me. And then when we look over here, our proposed outputs.shape, well, okay, they're 384, 128 by 512. And actually, that's the wrong shape for proposed outputs. If we think about that for a second, what we really want is our proposed outputs to be to tell us a probability for each of the possible words in our dictionary. So there are 256 words. So this should be 256. So let's think about how we're going to get there. Cool. So the next step is going to be the multi-layer perceptron. So we have something of batch, sequence, and embed. Then we're going to turn it into something of batch, sequence, and feed forward via a matrix multiply. By multiplying something of batch, sequence, embed, by feed forward, we reduce out the embed dimension. We'll cover matrix multiplies in more detail in a subsequent one. And then we introduce a nonlinearity. This nonlinearity is this lovely ReLU. And ReLU is just 0 if the number is less than or equal to 0, or the number if it's bigger than 0. This is a very standard ReLU, a very standard nonlinearity. Then we do another matrix multiply, add another nonlinearity, and so on. So we're going to do this first. We're going to do this multi-layer perceptron. Then we're going to skip attention today. We're going to just hold off on doing attention in this class, but do a whole deep dive on attention. And then we're going to generate output. So now we have something of batch by sequence by embed, and we're just going to send it back through an embed by vocab matrix. And that's going to give us something of batch, sequence, vocab. And that will be match our desired output. And then we're going to be ready to start thinking about our output. So I'm going to code up the rest of the neural net here. Again, feel free to hop in for questions, but I'll always happy to answer any questions. But the way we'll do this is for I and range, I think we have a layers constant already. Layers. Let's add a weight parameter, and we'll call the weight here feed forward. That seems good. And then we should give them each their own name. So feed forward, as we talked about, maps from the embed dimension to the feed forward dimension. So we'll call this one feed forward, and then we should really include the layer name in here. Cluster I, and we can get rid of this shape. And then all we're saying is that X should become JNP as array, feed forward, at X. Oh, excuse me, it's X at that, right? Because we put the contracting dimensions together. X at this, And then we'll update, then we will want to do a nonlinearity. So x equals jnp dot relu, jax on nn, so you gotta know where these live, I guess. X, and then we'll just do a second matrix multiply. Right, this is embed. Perfect. So now we have to reverse the dimension, right? Because now we're going, this one went from embed to feed forward. Now we want to go from feed forward to embed. Perfect. We're going to go to embed. We're going to do another relu. Perfect. And now we're in pretty good shape. And if we run the code now, what it should do is tell us, it should give us something of the same shape, but now there's something that's been pretty heavily processed by the neural net. Cool. So I'm going to just jump over to 93, see where we are there. And we can see, we can look at we can just poke around, propose output, that shape, perfect. And then we can also just look at our param. We haven't, so this is, again, batch, sequence, embed, which is what we expect. And we can look at our proposed param. So if we look at the keys in our params, okay, interesting, the first one's named params. If we look deeper, embedding, and we can just see these matrices. So we already defined this matrix, so it really shouldn't surprise us. But it's 2048 by 512, right? Because it's mapping. Because that's the mapping it's doing from a 2048 to a 512, right? Because embed, for whatever reason I call it that way, it maps from 2048 to 512. So that's the job of this matrix. Cool. So now we have to map into the vocab space. And as we talked about, we're just going to use the embedding matrix to do this, hopefully. We'll see if that works well here, actually. I don't know. So this matrix already has the right shape. It is already a vocab by embed matrix. So we'll just do jnp.asArray, excuse me. This one, we'll have to take a transpose because we want to map from embed to vocab. But we'll just do that. We'll put a transpose in there. And our output will be of the right shape. And it's a very common optimization that people will make this one different. But for example, Gemma, which is this big Google model we just launched today, publicly, is actually does exactly what I'm doing here. So different people have different assumptions, but I think there's no consensus on which is the best. Awesome. Cool. So now we get proposed outputs, and we can run this again. But what we'll find is that we're now outputting things, hopefully, in the right shape, right? So now we have, for every token, we're offering an opinion for that token for how likely each of the new letters is. It's not actually a probability though yet. So if we look at this guy, look at the shape, 384, 128, 256. It's 0, 0. If we just look at all the numbers, well, they are numbers, but they obviously could not be interpreted as being probabilities. So right, there's no such thing as negative probabilities, and they probably don't sum to 1. If we just want to see that, they sum to 0.3. Cool. So the next step, what we have to do is really two different things. We have to build our loss function, and then we have to decide how we'll use that loss function to drive gradients to make this process better. Let's just look at the notes, see what we have for this. So the key trick is called cross entropy. I wonder if this link would be good actually for us. Oh, probably not. And it's showing us the probability here. I actually haven't typed out my formula, unfortunately, so this might not read that too hard. But we're going to use this cross entropy structure to give us the loss. And cross entropy is actually a little bit tricky, so I'm not going to have us fully implement it. But I will show it to us. So the key to cross entropy is that you first do exponential of everything, then you do a sum, So now saying the sum of our exponentials is 854. And now for each index, you assign a probability based on its likelihood. So this one might be the 13th index. The 13th index is going to be proposed outputs exponential over this. And we're saying we're giving it this little probability, right? About 4/10,000ths. So that's all cross entropy is actually doing. But I think we'll just put it into its own little function just because it's a little tricky. And then also, I think we want to use the JAX cross entropy just because there are important numerics related to this particular thing. So calculate loss, inputs, outputs, and what we want to do. So there are a couple different things we have to do. So we have to do a one hot encoding. So this is called jax.nn.one-hot outputs, and then we need to use vocab div. So what this is doing, and I think I can just do it. We can see it here. Is our outputs were shaped as batch by sequence, and by doing this, now they're going to be shaped as batch by sequence by 256 by our vocab size. So that's just, and then and let me just really be clear, they're almost all 0, but it's saying what I really want is for this thing to output that index. So what all cross entropy is doing is say, well, the loss is going to be big if we assign very little value to this index, and it'll be small as long as we make this index value be big. So we'll do a one hot. And then it's just as simple as we have this function, optix, softmax cross entropy, oh, beautiful, logits. So logits are our inputs, and then we have to put one hot, which are our labels, and that's our loss. So this is computing this cross entropy that we just talked about. We can return that here. One hot, return loss, and then we can print our loss. Well, it's not going to be very good, but there's no reason we can't calculate it. Calculate loss, inputs, outputs, perfect. And we get a loss. Then why don't we just print out? We should probably have an iteration number. So iteration is 0, and we can just print out a map from iter to loss. And we will get rid of this breakpoint, and we should probably increment iter. Cool. So what this is going to do is not actually train the neural net, but just tell us how well we're doing right now. So we should see a bad loss, and then the loss shouldn't improve. The neural net is just making random guesses at this point. Rude. Assert type failed. So reading this through, it's telling us that it wants this to be a float.
Should it be swapped, Rafi? Because I think that it says inputs comma one hot, and if like is it reversed in that order or no?
I appreciate it. Unnormalized probabilities, but they want this to be a probability distribution, right? So I think they're saying that this should be a probability distribution, and I think if we can just jump in. I think what they're objecting to is that one hot is an integer, not a probability distribution. I believe that's what all this is saying. So we can just poke around after the crash. So inputs. Oh, much worse than that. So our inputs. Oh, these aren't proposed. We put inputs. We were supposed to put proposed outputs. Cool. Well, that's programming. So proposed outputs are our guesses. And we just need to make sure that our guesses are, we're passing in our guesses here. Cool. So hopefully we'll see this in a second, and hopefully it will produce it. Okay, so good news, bad news. We are producing losses, but I haven't averaged them. So there's like, this is a huge number of losses, and it would be a little bit better if we would just do this JNP.mean, so take an average of our losses, and that's how well we're doing on average. Awesome. Maybe I'll just break for questions for a second, then we can go back to the slides, and then we can do the next piece. Any questions how we're doing? So hopefully by this point we've seen kind of how we compute a loss, but we haven't yet seen how to optimize the neural net. So what we wanted to do is naturally drive it to improve the loss. And that's kind of the key missing piece for today. Zach?
Hi, Rafi. Just wondering why you're throwing in the jnp.asArray casts inside the Flex model.
I thought that they were necessary in Flax. Do you not need those anymore in Flax? They weren't.
I think it just comes straight up as a JAX array. Then there is also a mysterious flag for unbox true false, I think in param, which I think inherits from variable, but yeah.
I think that maybe it's if you use that flag, it doesn't work. That's a cool little improvement, by the way.
Oh, cool.
I always do that. I think it's if you use that mysterious flag that you need it. Cool. That's even better. I guess it universally works. Cool. Well, I'll simplify the code. Thanks for showing me that.
Anytime.
Cool. Any other questions? Awesome. So we just want to wrap this up. And what we want to do to wrap it up is the way neural nets learn is gradient descent. And hopefully we can find the slide. So what we want to do is do something like this, where we run the computation, we get the loss from the gradients. So the gradients show us how we can do better. And then we move a little bit in that direction. And then we move a little bit more in the direction. And then we just keep doing that. And that gets us closer and closer to the optimal point. And because we're doing it on batches of small batches of text, each of the gradients isn't perfect, but they tend to point in the right direction. So across time, they help us get to where we're going. So what I'll do here is just quickly show this off for folks. So rather than program this from scratch, though it's actually a really easy thing to program, so it could be a fun thing to do if people are interested in it. We're just going to bring in an optimizer, so the learning rate, and we will choose learning rate. I think I already have that as an n variable. Looks like I do. Perfect. So we have a learning rate. We'll make a train state. So this is a state that represents both our parameters and our loss, and our optimizer state. So model.apply params equals params. So this is all just creating this optimizer state. And we can poke into this optimizer state for a second as well. And then tx equals tx. So this is just telling it how we want to update. Okay, seems good. But we don't actually have a gradient function. So we're going to have to just do a little bit of rejiggering to get a nice gradient function. So we're going to have to give our inputs and our outputs here. We'll have to do our gradient stuff inside of our gradient function. So here, this is going to be params. We can take a model and inputs. Model. So I think we were applying as params inputs. Hopefully I transcribed that right. When we calculate the loss, model params inputs. Model params input outputs. Oh, perfect. And we don't have to propose outputs. That seems fine. So this code should run, though it's just a little refactor to really support the main goal. We shouldn't take proposed output, excuse me. And this is actually the heart of what makes JAX so powerful. So JAX, really, they call it NumPy with functional transformations. And really, what we have now is we've programmed the calculate loss. And what makes JAX cool, and PyTorch and TensorFlow can do this too, but JAX really describes it in a more controllable way. And we'll see why that's useful. So I'm actually this order here is we can literally just command PyTorch, command JAX to do this conversion for us. So we used to have this function calculate loss, and we'll just ask JAX, hey, JAX, I want the value, I want the grad. That's a function that takes calculate loss. And I think if it gives us a doc string, we can see that it defaults to taking the gradient with respect to the 0th argument. That'll do whichever you want. And we'll get a loss, we'll get a grad. And now all we have to do is have our state apply the gradients. And that is all it should take for the neural net to learn.
Yeah, I have a question. Is there anything special for LLMs or special considerations when it comes to selecting the loss function, the learning rate, those kind of parameters? Or is it just like the other neural net?
Yeah, no, I mean, I think it's definitely like other neural nets, but they are complicated to select. There was a lot of thought in what goes on to selecting a good learning rate. Loss function as well. Here we're using a very standard loss function, but you can also do different loss functions to better represent your tasks at hand. So lots of thought goes into that, but it's very similar to other neural nets. Okay, so our loss isn't going down, which isn't what you love to see. It turns out here what is happening is that I made a copy of the params inside of train state, but we didn't actually use them here. And then we were updating a different copy of the params. So I'll just do this state.params. And then hopefully now our model will in fact learn, right? So the loss starts out as being 6.3. Hopefully loss will now in fact come down. Cool. And the loss comes down. This is a very not powerful neural net. We'll learn part of why it's not so powerful in the future, but it pretty quickly is able to drive the loss, looks like, down to about 2, or maybe it's a little bit worse. Cool. So that's really everything I was hoping to cover here. I want to just tie it into the rest of the content that I'm hoping to cover over the next sessions. And then I think I'd love to answer any questions, and I will post suggested tasks if people want to dive a little bit deeper. So we implemented this LLM from scratch. We did skip attention, but we'll spend a whole session on that. But that's really what the class is about. I'm really here hoping to help people understand performance. So in the next one, this was all about program. The next one will be about predicting and profiling. So really understanding, actually for simpler systems in the LLM, just what goes on for a single chip to achieve good performance. Then we'll do the same thing in 2 classes from now for sharding. And then we'll go, so sharding means distributed computations across multiple chips. And then we'll have some follow-ups where we dive deeper into the various things. So both attention, really fixing this implementation to include attention, which is at the heart of a transformer, so the last missing piece. And then just spending a whole session just talking about analyzing trading performance, and a second session just analyzing inference performance. Cool, so that's what we have coming up. I'm happy to answer any questions, and if not, I think we can sign off here a few minutes early. Jet, are there any limitation on functions that JAX can auto-grad? Yeah, so there's definitely limitations. The type of thing that would be hard for JAX to auto-grad is if you have control flow that depends on a specific number. So if x is less than 3, do one thing, and if x is greater than 3, do another computation. So that type of computation can be hard for JAX to autograd. And hopefully as we go through this and understand JAX, how JAX works, that will be a little bit clearer. And I have a feeling Misty Ford is Sky, so let me just talk for a
fun
second.
fact about JAX, it actually can autograd through data-dependent control flow like that, but it cannot JIT. So, right, usually at some point we're going to JIT our function that's also being graded, and then it will indeed fail. We're actually thinking of removing that capability from grad because it would simplify some things in JAX, and then given that so many people JIT anyway, it's like, is anyone actually relying on the current behavior? Like Rafi didn't even know about it. So if anyone is using grad with data dependent Python control flow, let us know. That would be an interesting data point.
That's awesome. Glad to have you here, Sky. That I did not know that at all. And I think that I just want to be clear. JAX can in fact differentiate those functions. So just to answer Julie's question as well, continuous and differentiable. It turned out JAX can differentiate. Yeah, so max pooling is not differentiable. There are a number of non-differentiable functions that JAX can differentiate. There's a whole like field called like subgradients, which is a slight generalization of differentiability. So one function that's not differentiable that JAX can definitely differentiate is relu. So at this point, at 0, there are 2 separate gradients. So that's a good question. And then also both Sky and I were just crediting that you were using pure control flow. You can also put your control flow into JAX, and you'll be totally good. So there are a number of options. Like this is a really good question from Sky and Julie, from Jet and Julie. But JAX can do in practice a lot of differentiation for a lot of cases. Vaibhav?
Yeah, I was just thinking that the comment about the data dependent, control flow and incompatibility with JIT is basically not just for grad, it is true for any function. If you have a function with the data dependent control flow, then you should not be able to JIT that function.
Well, you can JIT it as long as you expose it to JAX, and we'll learn more about it in the future, Vaibhav. But you just have to be a little bit careful about how you do it.
Okay.
Cool. Sounds good. Sky, your hand's still up? All right, no comments from Sky. So cool. Hopefully this was helpful. I'll post. Were folks able to get into the Discord? I saw a lot of Discord drama. All right, perfect. Thank you for everyone who helped. Oh, Julie. Oh, not everyone's happy. Can someone post a good link again? Julie, I think there's some good links in the chat. I don't know which ones actually work. Maybe Jet, you can post again. Cool. Thank you, Jet and Sky. Well, I'll turn off the recording. I'll be around if anyone wants to chat for the next few minutes. Otherwise, thank you so much for joining and looking forward to chatting next week. I'll post some test your understanding exercises in the Discord. Bye, everyone. Stay on the line if you want to chat.